And let me thank the organizers, Gemma, Beth, David, and Hiroe for their very kind invitation. It's really wonderful to be here. The workshop is great. I learned a lot, and it's really great to see all of you again. Yeah. So today I'm going to talk about time parallel methods for optimal control problems. Under hyperbolic PDE constraints, that's the goal anyway. I'm just not saying that this is the last word, obviously. I mean, there's still lots to do. But the reason I want to talk about it is because, I was part of this joint France-Hong Kong project. And in fact, I've been invited for the past month or so at the Université Sorbonne Paris Nord in Paris to work on this project with Laurence Alberne, Bérangère Delhomme, Julien Salomon, who are all part of the project. The project finished late last year. And also there's Hong Yu Liu at City University of Hong Kong, who is the Hong Kong principal investigator. So we started this project, when I was just about to, move from Hong Kong to Canada. I'm still part of this project. And some of the work that I'm presenting is also, done by a postdoc, De Quang Bui, and a student who just defended last week, João Norberto Nyon. So, and now he's doing a postdoc in Orléans. And of course, Martin is around because he knows all of us. And, it's always lovely to talk to Martin. And Pierre-Henri Coquet is always. So even though the project finished about, it's 6 months ago, and of course, with these things, it raises more questions than we expected to answer. So I'm just showing you, what sort of results we've got and what we've learned from all this. So maybe just a brief recap of what the kind of problem we're thinking about looks like. So according to Glowinski and Lyons, what is optimal control? It's basically at a given time horizon, we want the system under study to behave exactly the way we want it or in a manner arbitrarily close to it. Okay, so in practice, mathematically, how we would formulate this is to say that I have a system here of ODEs or a discretized PDE that has some dynamics, and it takes some inputs, usually, oops, I'm sorry.
You want my stick? Or
yes, the stick would be very helpful. Thank you. So there would be some sort of a knob that we can play with here, which is like a control V, which goes into the input. Here it goes in additively just to simplify discussions, but in other problems, it could go into the coefficients, we could do other things. Okay, so this is a system that we want to steer towards a particular target, y tar, here at some finite time horizon, y at capital T. So this goes into my objective function that I want to minimize. I want to minimize the discrepancy. There might also be some target trajectory that I want to follow, though that would be a tracking problem. But of course, I also don't want to spend a lot of energy doing it. So I also penalize with the total cost of the control that I'm putting. And then I'm taking all this together, and this is the thing that I want to minimize. And then there's some weighting here, alpha and gamma, to see like how much I want to be close relative to how much I want to spend in energy. Okay, here there is an operator B here, which allows me to control over a subset of the,
It would be just nice to make a comment here that deep learning can be written exactly like this. When you said the coefficients could also be in the F, then it's a continuous version of a neural network that you train for an input-output thing.
There we go.
Wanted to make that comment.
So I'm doing machine learning. This is what
you're doing machine.
Yeah. Okay. So coming back to this B, so you can think of it as like controlling over some degrees of freedom, some subset. It doesn't go directly into the state. Or it can also allow me to rewrite, things that are second order, like the wave equation in terms of, the original variable and the time derivative. And there, if you want to put forcing in, you can't put it in both. So you have to put a 0 here. So the B also handles that kind of thing. Okay. This is closely related to inverse problems. You would be optimizing instead of a control that you put in, it would be like to match coefficients and stuff. So Sebastian Goetschel is going to talk about this a little bit. So, and then, so there, we can talk about approximate or exact control. So here, the optimal state does not necessarily have, y of t equals y tar. So you're only hitting the target approximately. Now, of course, if you try to crank up this alpha, if you're willing to, pay a lot to get very close to the target at the limit of alpha going to infinity, you would get what is called the exact control. You would try to land exactly at your target. Now, the existence of such a control, it will depend on the system. There are these controllability criteria that Kalman found out for the finite dimensional case, and then when it's a PDE, it's more complicated. I'm not going to get into all of that. So just to say that, in this talk, there's going to be some approximate control where alpha is finite, and then later on, I'm going to think about the exact control for the cases where this is actually possible, and that will change the problem slightly. So, so you would have, instead of having all these weighting terms, you would just have yt equals one target, and then that disappears from the objective function. And you can also limit, the admissible control as well, and then you would have, constraints on the control. I'm also not going to talk that much about that. This is very quickly going to go into like a linear thing that I can analyze. Okay. This is the fanciest simulation that you're going to see in this talk. So I have a wave equation in 2D with two initial, these are not sources, there's just initial bumps in the initial conditions. So if you just let it be, it's just going to expand, and then it's going to hit the boundary. It's going to reflect because I'm imposing Dirichlet boundary conditions, and it's just going to bounce around and do stuff. But I do want it to hit a target of 1 everywhere, so I'm willing to move stuff here in the domain in order to get that. So when I show you, this is the control, this is what I have to do to force my solution to be close to 1s everywhere. I just thought that's a funny thing to. So you see, it's like putting energy, it's not everywhere, right? Because that would be too expensive. So it just sort of makes a rectangle, and then it tries to like keep everything inside the rectangle the same. So this is the kind of thing that I want to calculate. Yeah. Okay. Oh,
So it made the wave a flat surface.
yeah, exactly. It won't do naturally.
It doesn't want to do that.
No, exactly. You have to force a lot. See, alpha is 10 to the 4 here. You're trying to force it, to the final state. Okay, so you have some optimality conditions. That's the fancy equivalent of, differentiate your function so they equal to 0. But then, we have differential equations. So, I mean, most of you are probably familiar with this, but just as a recap, so I have this objective function that depends on v and y, but y is a state that depends on the control itself. Okay, so the y, it depends implicitly on v. So if I just fold this into the objective function, I call it j hat, I want to look at its derivative or its gradient, whatever you want to call it. So then what you have to do is, you imagine you perturb your control by a little delta v, and then you look at how much the control, the objective function is changing up to first order. So you do this, and then you get an object like this. So it's of course going to depend on delta v. It's also going to depend on the perturbed trajectory delta y, either at the end of the horizon or everywhere. Okay, and that's inconvenient because every time I change a delta v, this thing's going to change. I want it in a more convenient form. So what I do is I write down the differential equation that delta y satisfies. It looks like this. I multiply it by an arbitrary function, which I call lambda, and then I integrate by parts. So there are some boundary terms coming out. There's no delta y of 0 because I'm not changing the initial condition. So that's just 0. And then now you get this minus lambda, the time derivative of lambda here in product with delta y. This thing I basically just pass the Jacobian of f on the other side, and you get something like this. And then what you see is that, I have some delta y of t terms, and I have some integral with delta y. Same thing here. So what I'm going to do is I'm going to identify these pieces. So this was arbitrary before, but now I want this thing to match this, and I want this thing to match this. So that gives me what is called an adjoint equation. I have a lambda being the adjoint state that satisfies a differential equation. and then with some final condition, so it's propagating backwards. And all this is set up so that this thing I can just substitute into these bits, and I just write it as, you know, the integral of B transpose times lambda in inner product with delta V. So then everything is just this thing in inner product with delta V. Okay, so this is the represent.
Why you match the terms? Because you managed without Lagrange multiplier to get the Lagrange equation.
Yeah, exactly. So this is basically like direct elimination. I sort of write down this thing and then I match the terms so that all this I can replace by this thing. So I just substitute. You can see that this thing is equal to this thing if the lambda.
This is this Gaussian elimination that's in the Lagrange paper.
Exactly. So I'm just eliminating. Yeah.
Okay.
Exactly. So and the thing that what that gives you, which is less obvious with the Lagrange multipliers, that this gives you the gradient even when V is not optimal. Yes. Okay, so you can use descent methods. You could do BFGS, conjugate gradient. You're gonna need this object. Yeah. Okay. So the point is, if I want to solve for the optimal control, then I have two coupled problems. I have the original state equation, and then I use this equals 0 to eliminate the V, and I just plug it in here. So, and I have some initial condition for Y, and then I also have some adjoint equation that propagates backward in time with the final condition. And these two things are coupled tightly. Okay. Yeah. And then, if you have control constraints and you, instead of having this equality, you're going to have some complementary conditions that you have to deal with. So to simplify the discussion, I'm just going to think about the unconstrained case. Okay. So as Martin mentioned, you could also have obtained, you could also have obtained this coupled system by just taking the Lagrange function and then differentiate. And formally, you'll get the same thing. But then it's harder to justify why that's, the gradient and all that. But it's still helpful to do this, especially, just as, just to derive the right equation. So I'm quoting Troch here. Lagrangians are also powerful tools in the formal Lagrange method. You can use that as a contingent means to derive optimality conditions that can be easily memorized. But then the application of the rigorous proof of optimality condition is then not so straightforward. So if you want to justify it, you have to do something else. So for example, if you want to do the same thing with the exact control, then it's a little bit less obvious to do it this way because you somehow the objective function doesn't have the y in it anymore. So it's a little bit bizarre to try to do it that way. So you take the Lagrangian, you derive the equation, then you try to justify it afterwards. So for example, you still have this V plus V is still equal to B transpose lambda, but then you have to say, if I'm not in the range of B transpose, and there's a piece that's in the kernel of B that's not doing anything when I'm putting it in the control. So I might as well eliminate that piece, and that's going to make my L2 norm go down. So the optimum must be that, it is orthogonal to the kernel of B, etc., etc. And then you get back this thing, and then you're allowed to write this down, and then you can prove everything else. But you have to jump through some hoops in order to get there. Okay. So that I already said. Okay, so these are the dangerous slides where I try to list people who worked on things. And of course, people in the audience have worked on many of these, and then I try to add them. And at some point, instead of the nilpotency, I had the number of references diverged to infinity, so I stopped. So I apologize if your name's not in there. But yeah, so basically, if you want to find the minimizer now, you have the gradient, so you can use any descent method. You can also solve directly the derivative equals 0. If the problem is linear, you just use conjugate gradient precondition possibly. Or you can write down the KKT system, the saddle point problem, and then try to do an all at once preconditioning, which many of you have worked on here. This is, of course, by no means exhaustive as a list. You can do multi-grid, you can do domain decomposition, you can do saddle point preconditioning. We have, lots of results on that. John has worked on that. And then if I want to do it in parallel, then you can take your descent method. You have to compute the gradient. So the gradient has the state in it, has the adjoint in it. So those are initial value problems. So now you are all experts on parallel and time for initial value problems. So use your favorite method, and that will give you some speed up. But of course, for hyperbolic problems that we know that there are known issues and there are now many known solutions. I really appreciated the talks this week on parallel and time of hyperbolic problems. So for example, parallel diac can work very well. Some multi-grid things, if you follow the characteristics, that works very well. So that's wonderful to know. Definitely things that, to keep in mind if you're solving these types of problems. You can also do space-time parallelism, SDC, and fast. And see, that's when I started giving up and say several. Okay. And then, for the wave equation, there are also specific things like temp pitching. You can do short waveform relaxation and pipeline, etc. But if you were to do these compute the gradient by integrating forward and backward separately, in some sense, you're breaking up the control structure. You're breaking up the forward-backward structure. So we're trying to take a different approach and say, instead of like separating them and then now you have to worry about all the characteristics, maybe it's better to just leave them as coupled things. And then in any case, you're going to have to iterate. So maybe there's some speed up that you can achieve that way. So for the rest of the talk, I'm going to consider them as coupled systems with the state and the adjoint. And I'm going to look at time domain decomposition methods for that type of problem. Okay, so here's my time horizon. There's in blue is the state that I'm trying to integrate, and then the red is the adjoint. So if I'm going to be at the exact solution, then I have some continuity conditions. These pieces have to connect up. So that's what I'm aiming for. Okay. So if you're a domain decomposition person, then the most a natural thing to do is to say, okay, I have my subdomains, which are my subintervals, and then when I iterate, when things don't match, you just give your neighbor new information, and then you iterate and you iterate. And that's basically the Schwartz method in time for control. The first time I've seen this is written in algebraic form by Barker and Stoll at a workshop in Switzerland in 2013. The paper came out in 2015. So you can write it in like in this paper, it's written in terms of matrix blocks and stuff, but you can also think of it in PDE form, which is basically exactly what I said. Take a subinterval, solve the forward-backward problem locally with initial conditions provided by the previous the previous iteration, the y from your left neighbor, and the final condition for the lambda from your right neighbor. And then you iterate, and then you pass new information to your neighbor, etc. Here, I wrote it without overlap, and the surprising thing was that it converges without overlap, which is very surprising for us. And so I'm going to come back to this in a little bit later. I'm going to write this in a slightly different form. Here, they're written in terms of like traces, but what I can do now is that in order to come up with the new, I'm going to do this. So my variables, my primary variables are the state and the adjoints at the interface points. And then to get the new data, I need to compute the action of the propagator, the forward and backward propagator within one subdomain, which takes data from the beginning, the y at the beginning and the lambda at the end, and then it either produces the new y or the new lambda, depending on whether I'm talking about P and Q. And then I just update the y and the lambda using these propagators. Okay, so I iterate like this, and then at convergence, what's going to happen is that this is going to be equal to this, and this is going to be equal to this. So if I subtract, I get the fixed point equation, and then at the fixed point, this thing is going to be 0. Okay. So now I can think of working with the fixed point equation directly instead of doing this iteration. I can use Newton's method, for example. So that's like an Aspen method trying to, not possibly non-linearly preconditioned Newton method. So that's what it is. And so you write this down, and this is an iteration, and the only problem is that, these derivatives are very expensive to calculate. So you make an approximation like in Parareal. You say, instead of calculating these on the fine grid, I'm going to solve the same problem but cheaper with a coarser grid or maybe a lower order integration. Okay. And then these are the pieces that I'm going to use for my approximate Newton method. Okay, this is called Parareal. So this is work that I did jointly with Martin Yander and Julien Salomon, and came out a few years ago. Okay, and essentially you're solving this thing with an approximate Jacobian. Think of it this way. In this talk, I'm absolutely not going to talk about how you're going to solve this and how to precondition this. There is work on this by the Belgian group, Arne Bouillon, Giovanni Samé, and that essentially uses techniques that are similar to paradiac. So they take the blocks, they make it alpha circulant, and then they do a Fourier. And it works very well for problems where you can diagonalize everything. And it's great. Okay, so that's one possibility. I'm more concerned about if you start running this iteration, what is the contraction factor? Because I'm approximating the Jacobian, so I no longer get superlinear convergence. It's going to go back to being linear. What is that rate? Does it converge smaller than one locally, et cetera, et cetera? So I'm more thinking about that. Okay. Just to show you an example of how the method works, as a nonlinear iteration, I'm going to do a Lotka-Volterra equation, and then so that's the exact. It's supposed to turn this way, right? It's a Lotka-Volterra. So it goes. So this is the trajectory I'm aiming for. I start here, I end here. I just do a dumb linear interpolation to initialize my iteration. So of course the trajectory at the first iteration looks nothing like it's supposed to be, right? But then if you iterate, second iteration, third, fourth, fifth, it's gonna find it eventually. I mean, it is a minimization algorithm. It's a Gauss-Newton. So then after 7 iterations, the eyeball norm looks good. Then convince yourself that things converge linearly, but it's not too bad. And then, of course, there's some slight deterioration as your coarsening ratio. This is the inverse of the coarsening ratio. So this last curve here is 1,000-to-1 coarsening. And that still kind of works, so it's not so bad. So yeah, it's fairly robust as a nonlinear iteration. Of course, now you have to worry about how to do the linear one. So there's a first result that was already in the original paper that says if you discretize everything by implicit Euler, I say implicit because there's forward and backward. So they're implicit both ways. You have to solve both ways. Okay. Then the contraction factor is bounded by this object. You see this alpha here. Alpha is the knob that I tune to get it to match closely or not. The larger the alpha, the more closely I want it to match. So for very large alpha, this is not going to work. So there's a restriction of alpha times delta t, where delta t is the time step for the coarse integration. For the fine integration, it doesn't matter. It can be as small as you like, but for the coarse integration, it has to be small enough relative to the regularization parameter, so that, and then once you have this criterion satisfied, then your contraction factor is less than 1, and it's bounded above by this factor. And that is, and the proof is valid for linear diffusive problems, and the spatial operator needs to be symmetric. It basically goes by diagonalization. Yeah, so as I said, you need an effective preconditioner to actually run the coarse correction, but we can do it. And there's some further analysis available by Norbert Tognon, who analyze a system where you have growing solutions. So here, I assume that all the eigenvalues of the spatial part is less than 0, so that things will never be growing, but this can also be done for the growing thing. So that's for backward Euler everywhere, okay? Sometimes you want higher order discretizations. So for wave problems, for example, Hans said that you really need to have like higher order things to have enough of accuracy to proceed. Otherwise, the diffusion or the dispersion is going to, well, dissipation or dispersion is going to kill you. So, and then we found the same thing. So we're more interested in, looking at whether we can get this to work for higher order discretizations in time. For now, I'm fixing the spatial discretization. I'm not touching that now, okay? So that's what we started looking. And then, so this is the joint work with Julien Salomon and Norberto Nyon that I mentioned earlier. So basically, the first thing that we needed to decide is how do you discretize the objective function? Because you can have like a fourth order Runge-Kutta thing for your state equation, but then if you're using piecewise constant for the objective function, you're not going to get fourth order convergence. Impossible. You don't have enough degrees of freedom. So you have two choices. You can optimize and discretize, optimize and then obtain this forward and adjoint ODEs as continuous objects, and then discretize those separately. You can do it. It has some advantages, but there's also a danger that was highlighted by Hager. It says it ignores much of the basic structure of the control problem, and then if you're not careful, you might run into stability problems. And back then they're doing the analogy with finite element methods. It says if you preserve the structure, then you run into fewer problems than if you didn't. Okay, so we made the choice of doing the other one, which is discretize and optimize. So which means I have to discretize the objective function, I discretize the ODE, and then that's a discrete optimization problem. I calculate the discrete gradient, and that gives me a discrete adjoint equation, which I couple and then I solve. That's the one that we're doing. Okay. So the thing is, there's an integral in my objective function. So in order to be consistent with the discretization scheme I use for my ODEs, what I'm going to do is I'm going to write any integral of this form as a differential equation whose derivative is just the integrand and starting with 0 initial conditions. And then what that allows me to do is to build that into as an extra state in my state equation, and then just step through using the same scheme, and then everything is consistent. And then my objective function is just the final state, one of the final states. So that's what we're doing. We are considering implicit Runge-Kutta methods because we still want to be able to integrate the heat equation without CFL conditions. So that's where we started doing. So we have an S-stage Runge-Kutta method of this form. I write down the stages. The next step is written like a, linear combination of the stages. And then now you see that, there can potentially be KNs on both sides. So now I have to solve a problem, and then I plug it into here, and that gives me this state equation. And then the control goes in here. And then if you take the discrete Lagrangian and then differentiate with respect to the control, you get this. So that allows you to eliminate the V's and plug it in here, provided the BJs are not 0. Okay, so if the BJs are not 0, so these are the final coefficients here, then you can write down a formula like this. You can write down a similar formula for the adjoint equation. Oh, now I'm not doing any tracking. I only have a final target. So that's why there's no y and y hat. Okay. So now I'm doing a special case. Okay. So here I assume that the BJs are positive. That allows me to write down this formula, but also it has been shown that if some of the BJs vanish, then there are issues with the discretization itself. The control may not converge to the continuous control. It's a nightmare. So it's a fairly natural assumption for this type of formulation, just to avoid any problem. Okay. So the real question now is, if I use, let's say, fourth order Runge-Kutta for my state equation to derive all this, do I get p-th order convergence to the continuous state and adjoint? And the answer is maybe. Actually, yes, but there are extra conditions to satisfy. Okay, so there's a theorem by Hager in 2000 that says if the Runge-Kutta method satisfies both the usual order conditions and some extra order conditions that are needed for the optimal control case. So you see there are extra equations, 1 extra equation for order 3, 4 extra equations for order 4. If you have these extra ones, then everything converges in the right order. Otherwise, you get an order reduction. Is that, yeah?
I can't imagine the quotients and the optimal control conditions make them nice to work with.
Yeah, no, so the proof is actually it uses a change of variables. So there are some like long calculations that shows you that these are the coefficients that you need to. So basically, the change of variables allows you to actually write down the adjoint equations as a backward propagating thing. And then if you want those to satisfy the order conditions for that equation, then those are where the extra conditions come in. They're not automatic.
So it comes from the adjoint.
Exactly, it comes from the adjoints. You have to satisfy the order conditions for the adjoint as well. Okay. And then a lot of schemes satisfy both automatic. Well, this one's order 2. There are no extra conditions. Of course, that's going to work. This one is order 3. It's an implicit one. It's a diagonally implicit one, and it satisfies the extra conditions automatically. This one does not. Okay, so a lot of them do, but not everything does.
Can we assume that implicit methods
No,
satisfy?
no, you actually have to check. It is possible to screw this up, actually, and we have done it, and we did observe the order reduction. I'm going to show you in a minute. Yeah, so these are not automatic, but a lot of the common schemes satisfy these.
Can I find a list of which ones don't?
Yes, I think there's a list probably. Yeah. So if you're careful, then yes, it converges in the right order. And so P0 is the continuous solution operator. This is the discretized one. Okay, so the theorem that we managed to prove about para-opt this time, about our optimization algorithm, is that if you use, so first of all, again, it's for a linear problem. So linearize everything before we start applying this. You discretize this in time by a Runge-Kutta method of order P that satisfies both the initial value problem and the optimal control conditions. Then the contraction factor is bounded by this object. So the main difference with the previous result is that there's a delta t to the power p here. So the order actually comes in. So if you use a higher order discretization, para-opt will converge faster. Okay. There's still a dependence on alpha here, so you're still not allowed to have like outrageously large alpha, making your course time steps small. But this is the dependence. Okay. And this result is more general in the sense that it doesn't use diagonalization. It's an operator type argument, so it also works for non-symmetric, non-self-adjoint spatial operators. And there's no there's no assumption that your solution has to decay. It also works for growing things. Well, the discretization has to be stable. If you take one time step, the change has to be less than like 1 plus a constant times delta t. It can't go completely unstable, but otherwise, this is how it goes. And you can interpret this sort of a condition in saying that basically this is the error of the course integrator. So this is how much mistake you're making in terms of like trying to find the target. If you multiply by alpha, that's your estimate of the control of the objective function, at least for the target part, and that can't be bigger than the L2 norm that you're trying to minimize in the control. So you see the weighting in front of the control is 1, and the weighting in front of the target is alpha. So that has to make sense. Otherwise, the inaccuracy in your course solver will overwhelm whatever you're trying to do. So that's the interpretation. So just a 2-line sketch of how this goes. You write down the iteration in matrix. It goes like, well, it looks like a difference between the fine and the coarse para-opt matrix, and multiplied by the inverse of the coarse one. The fine one looks like this. The coarse one looks exactly like this, except with a capital delta t. So you change these operators on the off diagonal. You see that when you subtract, the first row becomes 0 and the last row becomes 0 because there's no dependence on delta t. And then the difference between the two matrices is basically the difference of these operators, which we already know that it's order capital delta t to the power p, because you just compare with the continuous one. Okay. So we know that the difference here is bounded by order delta t to the power p. So the only thing left is to show that, you know, the whole thing is stable. So when you take this inverse here, it doesn't multiply things, you know, by a huge constant that you can't control. So this we do need to show, but you know, we did it, and that's where the alpha factor comes in. It comes from this stability estimate. Okay. Heat equation. This is the same example as in the first paper. 1D. Okay. This is the initial. Initially, there's one bump. You want to create two bumps instead of one. Okay. And then we're trying two methods. You know, the one that is third order in both the initial value and optimal control sense, and then the broken one, which is third order for initial value, but not optimal control. And you see that these slopes are exactly what it's advertised. You know, this one, you know, there's this delta t to the power 3 here, and this one is delta t to the power 2. I mean, it still converges, but it's not the third order that was advertised because there are conditions missing. And you actually see this in the convergence factors. Just to show you a slightly nonlinear one. Here, the control enters nonlinearly in this H thing. This is a quantum control problem. We call it Schrödinger type, but it's not a PDE, so it's not really the Schrödinger that we're used to. But it goes complex and it has like oscillatory behavior and all that. So here I'm running the fully nonlinear version of parallel opt, and then we see that here my coarsening factor is much less aggressive. It's, well, this one has no coarsening, so that's why it converges in like essentially one iteration. That's a true Newton method. And then, you know, the coarsening by a factor of 2 for H, and it's still converging roughly correctly. And then you see that, and then I'm using an order 2 method here. This is Crank-Nicolson. And we use Crank-Nicolson in order to preserve energy. So here the slope, it's a little bit hard to see, but it's kind of, it's order 2. Because Crank-Nicolson is order 2. So this is all well and good for a finite alpha. I'm doing approximate control. Now what happens when I try to do exact control? So this is the project with Laurence Bérengère de Lhomme and de Quambly. Basically, everything falls apart. So we were shocked and confused. So we decided to step back and say, okay, para-opt is maybe too complicated. Let's try to understand this thing. Let's go back to the Schwartz. Okay, instead of just trying to solve the fixed point equation by a Newton, let's just go back to the usual Schwartz thing. Okay, it's just to, you know, show you what the so right now, and then also wave was too hard, so we decided to do the transport, the advection equation. We didn't put a coefficient here. We're going to change the CFL later, so that's equivalence. Okay. So we put an exact target here, and the only thing left in the objective function is the control itself. Distributed control, so there isn't even a B transpose. V is just equal to lambda, so I'm just going to use V and lambda interchangeably. And then we can also use the method of characteristics to calculate the exact solution. Everything is known, so we were trying to understand what's going on, okay, basically. So we go back to our Schwartz in time. It looks like this. Of course, here there's no knob to turn. There's no coefficient. It converges or it doesn't converge. There's nothing we can do. So let's give ourselves some room of maneuver. Let's try to put some coefficients here. So what I did is, instead of just having a y equals the previous y, lambda equals the following lambda, I'm matching linear combinations of the state and the adjoint. And I control the proportions by these parameters P and Q, which I can tune to try to get the thing to converge. So these are optimized conditions. Just a word about these optimized conditions. So these are not completely new or, you know, or out of nowhere. This has already been used back in 2003 by Laniese and Leugering in order to solve a wave problem. Wave control problem. So, so these are known. We think of them as Robin conditions because if you remember the lambda appears here. So it's equal to a time derivative plus stuff. Okay, so it's like it's like a derivative plus the function value in the time direction. So we like to think of them as Robin conditions, but they also don't behave exactly like it because it's a control problem. It's different. Okay. Also, the problem is well posed because you can rewrite the problem as an optimization problem where you just change the objective function by adding these terms. Okay, so the P and the Q comes here, and basically you're trying to minimize both the control and some mismatch between the initial and final conditions and some given values. Okay, so it's a nice convex problem that is well posed, and you can use your favorite optimization code to solve this. So and then the whole game is to tune these P's and Q's in order to get fast convergence. Okay. We've tried this for dissipative problems, for example, a discretized heat equation, and there's a way of choosing these so that it's robust with respect to the discretization parameter, etc., etc. Let's go back to our transport problem because now there's new behavior. Okay. There's a wonderful theorem that says for the continuous problem, there are ways of choosing these P's and Q's so that I get convergence to the exact solution in a finite number of steps, and more precisely, the same number of steps as there are subintervals. Okay. And the proof is actually not that hard to understand. So the first thing is you write down the iteration matrix, but working on the Robin traces, on the things that you're actually passing around, the linear combinations. Okay, so you imagine each subinterval has 2 traces associated with it. So that's your input. And then after one iteration, you do some calculations and then you pass the right traces to your neighbors. So there are non-zero blocks at these positions and everything else is 0. Okay. Now you choose your parameters, P's and Q's, so that some of these blocks are 0. And it has to be exactly these ones. It can't be in the wrong position. Otherwise, it doesn't work. Okay. So because such a choice is possible, you have to show that such a choice is possible. Then your iteration matrix looks like this. And now if you square this, these bands sort of go farther and farther and then they disappear. So this is a nilpotent matrix. So I do have some nilpotent things on the slide. It's not that the slides themselves have disappeared. Okay. And then you see that, after 4 iterations, everything disappears. And then you have exact convergence. Okay. Now, when we were very happy, this is something that works really well. And then we try to implement it. And then everything falls apart again. So the theorem is verified when delta t is equal to delta x. When CFL is equal to 1, life is beautiful. And that's because everything is exact. You're just running the continuous case. As soon as CFL is less than 1, that's when things start to go wrong. It turns out that, and then things start to go wrong, so we step even further back 2 subdomains. Okay, not even n subdomains. So in 2 subdomains, your iteration matrix has just 2 blocks. And then you can diagonalize these because we use periodic boundary conditions. Just do Fourier. And then you look at each mode separately. And then you realize that your matrix now looks like this. These coefficients can be written in this form with some functions, phi and psi, that depends on the frequency. And it changes. These are not constants anymore with respect to frequency. So then you can't just choose the same P to make everything 0. And then it's finished. So you can't make that block 0. That's the problem, actually. Okay. And that's really because, these things depend on the dissipation of the scheme, and the dissipation is non-constant with respect to the frequencies. Okay. So yeah, so now what to do? Well, we can minimize the spectral radius. And even though it's not 0, let's try to do the best possible. Okay, so that's what we did. So in order to, so we've actually worked on both the P not equal to Q case and, P equals Q case. I'm just gonna show you the results for when the parameters are the same. Okay, there are more details in our preprints. Okay, so here comes Kwang, who meticulously estimated, these coefficients and what eigenvalues they give. The gist of it is the product of these two coefficients can either be positive or negative. When it's positive, you get real eigenvalues, and when it's negative, you get purely imaginary eigenvalues. And that depends on what parameter P that you choose. Okay, so the square of the eigenvalues looks like this. Okay, well, that's the spectral radius. So if your P is too small, then you just get plus and minus 1, and then you get no convergence. And if you choose P a little bit bigger, you get this cross thing. And then at some point, like everything lines up on the imaginary axis. The spectral radius is still quite bad. And then at some point it becomes a cross again. And if you try to make the two arms of equal length, then everything fits neatly into a circle, and that's your spectral radius. And that's the best you can do. Okay, so this is the optimum. Okay, and then if your P is too large again, one of the arms gets bigger again, and then it's finished. And it's not optimal. Okay, so there's a theorem that depends on like all these estimates with the low and the high frequency. There's a very long calculations. I don't know how he managed to do it, but it's unbelievable. So this is great. That's the good news. We have an estimate. The bad news is as we refine the time step. This is not the time step. This is just, the capital T is just the length of the subintervals. It's this one that you need to look at. As we refine the grid, the convergence rate deteriorates, goes to 1. We're like, actually, initially we thought that it wasn't so bad because for elliptic problems it does this. And then I said, no, I did it for the heat equation. It doesn't deteriorate. Let's work a little bit harder. So what you can do is you can introduce a relaxation parameter. So instead of just matching left traces and right traces, I can say I'll only take part of the new left trace, and then I just add complete the remainder with the old trace. So just do a relaxed version of it. Then you can work out the iteration matrix. It's just the 1 minus theta times the identity plus theta times what I just showed you. And then now you can play the same game again, find the P to minimize the spectral radius of this guy now, and also with the right theta. And then it turns out that now it doesn't deteriorate. And also the parameter is different. See, this is a constant with respect to delta t, whereas previously, this thing scales like 1 over square root of delta t. So you need to pick a different parameter if you want to use relaxation. So it's not the same behavior anymore, but this is of course much better, right? As you refine, it basically, the contraction factor is 1 over square root of 2, 0.7. It converges to that. Okay, so that's good news. So let's try this on a test problem. This is the initial condition, and we want to change the frequency at the final condition. So there are more peaks here than originally. And with a CFL of 1/2, so we're not just solving the exact problem. Okay, so if you plot numerically the contraction factor, it looks like this. And then the theorem says pick this if you don't use relaxation. So now this is pretty close. So our theorem is valid. And then when you introduce relaxation, there's the theta, the relaxation parameter here, and then there's the P, the Robin parameter here. So now we're a little bit off, but we're still in the 0.5, which is 1 over square root of 2 squared. So we're still pretty close. And then as we refine the numerical minimum is going to go towards this point. Okay. And this one is uniformly bounded away from 1. So this is great. And then you can really see this, when you actually run the experiment, with relaxation, it really converges much faster than without, even at a relatively coarse discretization level. So if we're going to use relaxation, we might as well, put Krylov on it and see what happens. It was going to be like the one last numerical experiment, and then we finish and submit the paper, right? There's yet another surprise, which is if you use 1/, the previous parameter that I showed you, it doesn't give the best behavior. And the reason is, well, it's Krylov, it's GMRS, so it doesn't work the same way. You don't just look at the spectral radius. How things are distributed actually matters. And in fact, this is more favorable for GMRes than this or something that looks like this. Okay, so basically you have to embed the thing. I mean, one way of estimating convergence is you embed this into an ellipse, and with the dimensions of the ellipse, you choose a good Chebyshev polynomial that gives you some sort of contraction factor. So that's what we did. That's basically, that comes from SOD. So we did all the calculations, and it turns out that this is the best case when you use GMRes. So there's another theorem that says, essentially, if you use GMRes, pick 1/. So this is the same parameter as the continuous case. So now we're coming back full circle. If you use the continuous parameter, it works well for the continuous problem. It works very poorly for the fixed point iterations for once you discretize. But if you use GMRes, that's the same one that you should use. Is it a coincidence? I don't know. Maybe, maybe not. Maybe there's a deeper reason. We're still at it at this point. So, there are these estimates that you can find in Sod's book, and then it turns out that P=1 gives the smallest bound. And it really does make a difference, yeah? So this is 1/, capital delta T. This is the continuous parameter. This is the optimized parameter with relaxation. See, it's already a little bit worse. And then, this is the optimized one without relaxation, which is like so far. And this is all Krylov accelerated. None of these are fixed point. I basically just use that parameter and then wrap Krylov around it, and there's still a difference. And then you can say, yeah, well, SOD just gives you a bound. Is it actually sharp? Well, it's not that sharp, but even the numerical one tells you that this is really the best one that you should use. So that's where we are. I mean, it's still work in progress. I mean, so now basically we have a bunch of lessons learned. So discretization completely changes the behavior because it changes the dissipation and dispersion of the scheme. It no longer matches the continuous problem. So you can't take it for granted that the results you derive from the continuous case will carry over verbatim to the discrete case, especially for hyperbolic problems. It feels that, when you have parabolic things, then at least the spectrum is real, and then you can argue that, the Krylov just centers it and then gives a little bit of acceleration. When your spectrum is like a cross, or even worse, if you have multiple subdomains, it looks like a star, then you really can't do this. So you really have to be careful. And then here, if you think about it, Schwartz is a preconditioner to the fixed point problem. But then for the fixed point equation. But the fixed point equation is a saddle point problem. And then you're trying to use like sort of time domain decomposition. So you're splitting it up into little indefinite blocks. So you're preconditioning something indefinite by something indefinite. That gets complicated. So it's also not trivial to do this. So like all the standard DD arguments about spectral bounds and stuff, a lot of them don't apply. So what works in our experience, like if you can diagonalize and use Fourier arguments, do it. If you can't, there are also energy estimates, then you won't get very sharp bounds, but at least you'll get some. And then finally, conservation of the control and optimization structure is crucial. So Para-opt for approximate control, we have a new result for a higher order discretization. We've explored a lot of what can happen with a pure transport problem, pure hyperbolic problem. When you discretize, all sorts of complications happen. You have to be careful. Then basically that leads to a bunch of ongoing work. Like well, first of all, the preconditioning the para-opt when you don't, when things are no longer symmetric, no longer normal, is still open, I think. Study the spectrum of para-opt for transport and waves. We've only have a few numerical experiments. We want a detailed study, some analysis for that. Boundary control is an interesting one. even if you have like smooth initial and target states, these things spontaneously generate discontinuities, and that's very bad for anything that has like dissipation and dispersion, especially. So there are techniques like by group filtering, etc., that you could do. Maybe yeah. So we're still exploring that with the Pierre Henry. Maybe we should really build in, like, enrich the discretization to really follow the discontinuities. Maybe that'll give us something better. Oh, that's waves. There's a. Okay. Thank you very much. Thank you.